Start with a simple question. Where is Earth right now? You might think the answer is obvious. Earth orbits the Sun, 93 million miles out, tracing the same path it always has. But that answer is missing almost everything that matters. Earth is spinning on its axis at over 1,000 miles per hour at the equator. It's circling the Sun at roughly 67,000 miles per hour. The entire solar system is orbiting the center of the Milky Way at around 500,000 miles per hour. And the Milky Way itself is drifting toward a structure astronomers call the Great Attractor at speeds exceeding 1 million miles per hour. Stack all of that together, and Earth is never in the same place twice. Not for 1 second. Every position it occupies is already gone the instant it happens. Here on the surface, you never notice any of this. You wake up. The ground is where you left it. Your house hasn't moved. That's because everything around you is moving together. You, your house, the atmosphere, all riding along at the same speed in the same direction. Relative to each other, nothing has changed. But relative to the rest of the universe, you've traveled an almost incomprehensible distance since the last time you fell asleep. In a single day, Earth moves about 1.6 million miles along its orbit. In a year, the solar system travels more than 4 billion miles through the galaxy. None of that motion is something you can feel, but it matters enormously the moment you leave the bubble of things that are moving with you. Home isn't a fixed dot you can point to. It's a location defined by a web of relationships, all of them constantly shifting. And once you're far enough away, that web stops giving you anything to hold on to. Now think about what navigation actually requires. To find your way anywhere, you need at least one of two things: a fixed reference point to measure your position against, or a precise, unbroken record of every movement you've made since you started. On Earth, we have both in abundance. Satellites in known orbits, landmarks that don't move on human timescales, magnetic fields, star positions that are effectively fixed over a human lifetime. Even far out in the solar system, we still have something close to a fixed reference: the Sun. Every planet, moon, and spacecraft is orbiting that one dominant point of light. Spacecraft like Voyager and New Horizons navigate using something remarkably similar to how sailors once used the stars. Cameras photograph the positions of well-cataloged stars. Software compares those positions to a stored map. Mission control measures tiny shifts in angle between the spacecraft, the stars, and known objects. From that, they can calculate exactly where the spacecraft is, sometimes to within a few miles, even billions of miles from home. This works because from a human time scale, stars appear frozen in the sky. Their true motion, called proper motion, is real, but so slow it takes decades or centuries to become noticeable. For navigation purposes close to home, you can treat the stars as fixed. But that trick has a limit, and once you cross that limit, everything changes. Every method we use to locate a spacecraft depends on comparing its position to something else. The deeper into space you travel, the fewer useful reference points remain, and the ones that do remain become less and less precise. Take radio tracking, one of our most powerful tools. NASA's Deep Space Network, a system of massive dish antennas across California, Spain, and Australia, tracks spacecraft by sending a radio signal out, waiting for it to return, and measuring the round-trip time. Radio waves travel at the speed of light, and that speed is a known fixed number. So distance can be calculated from travel time alone. Engineers also measure the Doppler shift of the signal, the way its frequency stretches or compresses based on whether the spacecraft is moving toward or away from Earth. And that reveals velocity. Combine distance and velocity over time, and you get a remarkably accurate picture of where a spacecraft is and where it's heading. This is how we know, at almost any moment, exactly where Voyager 1 is, more than 15 billion miles from Earth, drifting through interstellar space. But notice what this method depends on. It depends on Earth. A signal traveling back and forth between the spacecraft and a fixed set of antennas on our planet. And that dependency is exactly where the problem begins. The speed of light is fast, 186,000 miles per second. Fast enough that on Earth it feels instantaneous. But space is vast enough that even light starts to feel slow. A radio signal takes about 8 minutes to reach the distance of the Sun. It takes over 23 hours to reach Voyager 1. Send a message, and you wait nearly 2 days just for a reply. Now imagine a spacecraft genuinely out in interstellar space, years or decades from home at any realistic travel speed. At that distance, round-trip communication time isn't measured in hours. It's measured in years. By the time an answer arrives, the situation you asked about no longer exists. The spacecraft has moved. Its surroundings have changed. Any guidance from mission control is already outdated the moment it arrives. This is the first wall you hit when navigating deep space. Earth cannot help you in real time. Every signal from home is a message from the past. So if radio contact becomes useless for real-time navigation, what's left? The obvious answer is dead reckoning. Keeping careful track of your speed, your direction, and how long you've been traveling, then calculating your position from that. Sailors use this for centuries. But dead reckoning has one fatal weakness. Errors compound. Every small mistake in measuring speed, every tiny miscalculation in heading, every unaccounted force acting on the spacecraft adds to the last one. On Earth's oceans, over a few weeks, that error might add up to a few miles. Annoying, but recoverable. Now stretch that same principle across a journey lasting decades, covering trillions of miles through an environment full of forces we can barely predict. Solar wind pushing unevenly against different parts of a spacecraft. Faint gravitational tugs from distant stars. Tiny thruster inefficiencies. Micrometeorite impacts too small to detect, but large enough to nudge a trajectory by a fraction of a degree. None of these forces are individually significant. But dead reckoning has no way to correct for what it doesn't know it's missing. Over interstellar distances, even a rounding error measured in fractions of a degree can translate into a position error measured in millions of miles. A fraction of a degree held constant over 4 light-years of travel can shift your final position by a distance greater than the size of an entire star system. You wouldn't just miss your destination. You might sail straight past it without ever knowing it was there. So dead reckoning alone isn't enough. You need external references to correct your position along the way. And here deep space navigation runs into its second major wall. The stars, the ones we use so reliably near Earth, stop being reliable the farther and faster you travel. 2 problems appear at once. The first is stellar aberration. If you're moving at a significant fraction of the speed of light, the apparent position of every star in the sky shifts. The same way rain appears to fall at an angle when you're running through it, even though the rain is falling straight down. Your motion distorts how you perceive it. At even a modest fraction of light speed, the entire sky would appear to warp, with stars bunching up ahead of you and thinning out behind. Every reference point your navigation system depends on would be displaced from where your charts say it should be. And the amount of displacement changes constantly as your speed changes. The second problem is proper motion. The slow drift of stars across the sky that we normally ignore because it's too small to matter over short missions. Stretch a mission out over decades or centuries, and it stops being irrelevant. Stars you charted your course by at the start of the journey will have shifted. Some by a small amount, some by a great deal, depending on their distance and true velocity through the galaxy. Your star map, the very thing your navigation depends on, becomes slowly, quietly wrong the longer you're traveling. And there's a deeper issue underneath both of these. Distance itself becomes hard to judge. Near Earth, we measure the distance to nearby stars using parallax, the tiny apparent shift in a star's position when viewed from two different points in Earth's orbit. It works beautifully for stars within a few thousand light years. But the farther away a star is, the smaller its parallax shift becomes, until eventually it's too small to measure at all. Now imagine measuring parallax not from Earth's orbit, but from a spacecraft moving at a fraction of light speed, with your own baseline constantly changing in ways that are difficult to calibrate. Every fixed point you thought you had becomes uncertain. Every star you use to check your position is itself shifting, both because it's genuinely moving through the galaxy and because your own motion is distorting how you perceive it. This is the deep irony of deep space navigation. The tools that work so well close to home, the stars, radio contact, dead reckoning, all begin to fail simultaneously the farther you go. Not because engineers were careless, but because those tools were never designed for the scale, speed, and duration that true interstellar travel demands. So what alternatives have scientists proposed? One of the most promising ideas is called pulsar navigation. Pulsars are the collapsed cores of massive stars that exploded as supernovae. They spin incredibly fast, some rotating hundreds of times per second, sweeping a beam of radiation across space like a cosmic lighthouse. Certain pulsars, called millisecond pulsars, are remarkably stable, ticking with a regularity that rivals the best atomic clocks on Earth. The idea is elegant. If you can detect the timing of pulses from several pulsars scattered across the galaxy, and you know their positions and rotation periods precisely, you can calculate your own position in three-dimensional space. The method compares the exact arrival time of each pulse at your location, similar in principle to GPS, except instead of satellites orbiting Earth, your beacons are collapsed stars thousands of light years away. NASA actually tested a version of this concept. An instrument flew on the International Space Station designed to detect X-ray pulses from known pulsars and calculate the station's position using only those signals. It worked, placing the station's position within a few miles of its known orbit, entirely through starlight from collapsed stars. A genuine milestone. But pulsar navigation isn't a perfect solution. The X-ray signals from distant pulsars are extraordinarily faint by the time they reach a detector. Gathering usable data requires large sensitive instruments and long observation times. A spacecraft moving quickly and needing frequent position updates can't always afford to spend hours patiently listening for faint pulses. Pulsar timing must also account for the same relativistic distortions, aberration, time dilation that complicate everything else at high speed. There's a longer-term issue too. Pulsars slow down gradually over time as they radiate away energy. Their timing, while remarkably stable over years and decades, isn't perfectly stable over centuries and millennia. Any navigation system built around pulsar timing would eventually need recalibrating based on updated models of how each pulsar is slowing down. Models that themselves carry small uncertainties. It's genuinely one of the best ideas anyone has proposed for interstellar navigation. But it's not the flawless cosmic GPS it's sometimes described as. It's another imperfect method, layered on top of several other imperfect methods. In deep space, that's often the best you can hope for. Now let's talk about a problem that goes even deeper than instruments and calculations. One baked into the structure of space and time itself. If you were traveling fast enough to make an interstellar journey survivable within a human lifetime, you'd need to travel at a significant fraction of the speed of light. And at those speeds, time itself stops behaving the way it does in everyday life. This is time dilation, one of the strangest and best confirmed predictions of Einstein's theory of relativity. The faster you move relative to something else, the slower time passes for you relative to that other thing. At everyday speeds, this effect is meaningless, but at a significant fraction of light speed, it becomes dramatic. Travel at 90% of light speed, and for every year that passes for you on board, more than 2 years pass back on Earth. Travel at 99% of light speed, and roughly 7 years pass on Earth for every single year you experience. This means something unsettling. Even if you solved every navigational problem perfectly, even if you knew with total precision exactly where you were and exactly how to point your ship back toward the solar system, the place you'd be returning to would no longer be the place you left. Depending on how long and how fast your journey was, decades or even centuries could have passed on Earth by the time you made it back. The people you knew would be gone. The cities you remember would have changed beyond recognition. In a very real sense, home wouldn't just be hard to find. It would no longer exist, not as the place you left. You could correct for Earth's orbital motion, for the sun's movement through the galaxy, for every gravitational influence along the way. And you'd still arrive at a version of home that has nothing left in common with the one in your memory. This is perhaps the most unsettling part of the entire problem. Even a perfect navigational solution wouldn't be enough. Because the thing you're trying to return to isn't just a location. It's a location at a specific moment in time. And that moment is gone the instant you leave it behind. Let's think about the scale involved, because numbers like these are almost impossible to feel intuitively. 4 light years, the distance to the nearest star beyond our sun, is roughly 25 trillion miles. An error of just 1 degree, held constant over that distance, would put you off course by more than 400 billion miles. That's not a small correction. That's missing your destination by a distance wider than our entire solar system. Now scale that thinking down to the problem of returning home. Your instruments, your star charts, your dead reckoning calculations, your pulsar timing, all of it carries tiny individual errors. Compounded across years of travel, the region of space you'd need to search to relocate Earth could be staggeringly large. Not a few miles, not a few thousand miles. Potentially an area so vast that finding one small blue planet inside it would be like trying to find a single grain of sand somewhere within an entire ocean, without knowing which ocean you're looking in. And you wouldn't have real-time help from Earth to narrow that search. Every correction signal sent to guide you home would already be years out of date by the time it reached you. This is why the phrase, turning around and heading home, carries far more weight than it sounds like it should. It's not a simple maneuver. It's an entirely new navigational problem, arguably harder than the outbound journey. On the way out, at least, you're heading toward a destination that hasn't had time to drift far from where your calculations expected. On the way back, everything you're aiming for has kept moving the entire time you were gone. And your only information about where it's gone is old, uncertain, and growing staler by the day. There's also a more immediate physical dimension to this problem that's easy to overlook. Human orientation depends heavily on visual and physical cues that simply don't exist in deep space the way they do on Earth or in low orbit. Astronauts on the International Space Station, despite being weightless, still have a nearby planet to look at, a horizon, sunrises and sunsets every 90 minutes, and constant radio contact with mission control just a fraction of a second away. Deep space offers none of that. No up, No down, no nearby horizon, no passing landscape to judge your movement against. Stars all appear to sit at the same infinite distance, whether they're 4 light-years away or 40,000. Without instruments, a person floating in deep space would have absolutely no way to sense which direction they were moving, how fast, or whether they were moving at all. Historically, disorientation of this kind has proven to be one of the most psychologically taxing aspects of extended space travel, even on missions that never leave Earth orbit. Extend that disorientation across the true emptiness of interstellar space, and every scrap of positional awareness has to come from instruments, calculations, and models filtered through imperfect data. Never fully certain. Let's go back further, because the idea of a fixed point in space isn't just a modern engineering problem. It's a question physicists wrestled with for centuries. In the late 1800s, scientists believed the universe was filled with an invisible medium called the ether, a fixed background against which all motion could be measured. If it existed, you could measure your speed against it, the same way you can measure your speed against the ground. Two scientists built an extraordinarily sensitive instrument designed to detect tiny differences in the speed of light, depending on which direction it traveled relative to Earth's motion through this supposed ether. The result, again and again, was nothing. No difference at all. Light moved at exactly the same speed regardless of direction, regardless of how Earth was moving. The explanation that eventually emerged overturned the entire premise of the search. There was no ether. There was no fixed background. There was no universal frame of reference against which absolute motion could be measured. Motion only makes sense relative to something else. There is no such thing as standing still in any absolute sense. This isn't just abstract physics history. It's the deepest reason why finding your way home in deep space is so difficult. It's not simply that our instruments aren't good enough yet. It's that the universe itself was never built with an absolute reference frame in mind. Now bring that same idea down to something familiar, something almost everyone carries in their pocket. GPS works so effortlessly that most people never stop to think about how remarkable it actually is. A network of satellites orbits Earth at an altitude of about 12,000 miles. Each one carries an atomic clock precise enough to lose less than a second over roughly 3 million years. Each satellite constantly broadcasts its exact position and the time that signal was sent. Your phone receives signals from several satellites at once, measures the tiny differences in arrival time between them, and triangulates its position. It's an elegant system. It works because every part of it satisfies a condition that deep space simply doesn't offer. The satellites are close. Their positions are known with extreme precision at all times. There are enough of them visible from any point on Earth's surface. And crucially, the whole system operates with communication delays measured in milliseconds, not hours or years. None of those conditions exist once you leave the solar system. There's no network of precisely known satellites surrounding you. The stars that might serve a similar role are light years apart. Their signals take years to update, and their apparent position then shift the faster you travel. You could, in theory, imagine a future where humanity has placed navigational beacons throughout nearby interstellar space. Artificial satellites broadcasting known positions the way GPS satellites do. But building and maintaining such a network across light years of empty space, keeping every beacon precisely calibrated over centuries, remains far beyond anything current technology could realistically achieve. There's another layer to this problem that rarely gets discussed: Earth's magnetic field. Generated deep within our planet's molten outer core, this field extends far beyond the surface, forming a protective bubble called the magnetosphere. It's been used for navigation for thousands of years. But Earth's magnetic field only extends so far. Beyond it lies the heliosphere, a larger bubble carved out by the solar wind, extending roughly 11 billion miles from the Sun, far beyond the orbit of Pluto. Voyager 1 crossed that boundary in 2012, becoming the first human-made object to enter true interstellar space. Once a spacecraft crosses that boundary, every trace of familiar locally generated magnetic structure disappears. The interstellar magnetic field that exists out there is faint, complex, and shaped by forces entirely unrelated to our Sun. It offers nothing resembling the reliable, well-mapped magnetic field that guided sailors and pilots across Earth for centuries. Any future traveler passing into that region loses yet another tool that worked reliably closer to home. Now consider the instruments spacecraft carry to measure their own motion directly, without relying on any external reference. These are called inertial measurement units, gyroscopes and accelerometers that detect changes in orientation and velocity. If you know your exact starting position and can measure every single acceleration and rotation afterward, you should be able to calculate your current position purely through internal measurement. No need to ever look outside. This purest form of dead reckoning has been used successfully for decades, guiding missiles, submarines, and early spacecraft. The Apollo missions relied heavily on it, with gyroscopes tracking orientation throughout the journey to the Moon. But even those systems required regular correction using star sightings, because gyroscopes drift. Tiny imperfections in their construction, tiny amounts of friction, tiny sensitivity to temperature changes, all cause small errors to creep in over time. For a 3-day trip to the Moon, this drift was manageable. For a journey lasting decades, crossing trillions of miles, that same drift would become catastrophic. Even the most advanced modern gyroscopes would accumulate enough error over years of continuous operation to throw a spacecraft's calculated position off by an amount far too large to ignore. There is currently no gyroscope, no accelerometer, no inertial system built by humans capable of maintaining useful accuracy over the timescale a true interstellar journey would require, not without frequent correction from some kind of external reference. And we've already seen how difficult, delayed, and uncertain those external references become the farther you travel. Just keeping our existing deep space missions on course already takes tremendous effort, and shows exactly how layered this problem really is, even at distances that are, cosmically speaking, still extremely close to home. New Horizons, the spacecraft that gave us our first close look at Pluto, required several small trajectory correction maneuvers throughout its 9.5-year journey. Each one was calculated by teams on Earth using radio tracking data, then transmitted as a precise sequence of thruster firings. New Horizons had all of Earth's tracking infrastructure, all of our accumulated knowledge of orbital mechanics, and clear, unbroken radio contact throughout. It still needed constant careful correction to arrive at its target with the precision required. And Pluto, despite feeling impossibly distant in imagination, is only about 4.6 billion miles from Earth at its farthest. A distance light crosses in a matter of hours. Scale that same need for constant correction up to a journey spanning light years, where correction signals take years rather than hours to arrive. And the scope of the challenge becomes almost impossible to overstate. There's yet another subtle distortion that would confuse any traveler moving fast enough for relativity to matter. It involves color. As an object moves toward you, the light it emits shifts toward the blue end of the spectrum, blue shift. As an object moves away, its light shifts toward red, red shift. At a meaningful fraction of light speed, stars ahead of you appear dramatically blue shifted, while stars behind shift toward red. A star that should appear as a familiar reddish or yellowish point of light might instead appear brilliant blue, its true color completely disguised by your own speed relative to it. Identifying stars by their expected color, one of the ways astronomers catalog and recognize specific stars from great distances, becomes unreliable exactly when you'd need it most. During the highest speed phases of a long journey, every method of visual identification becomes distorted by the simple fact of moving fast enough to make the trip survivable. There's also the environment itself, quietly working against long-term precision. Interstellar space isn't a perfect vacuum. It contains sparse but real amounts of gas and dust, along with a steady bombardment of cosmic radiation. High-energy particles racing across the galaxy for millions of years, some originating from ancient supernova explosions. Over years and decades of exposure, this radiation degrades sensitive electronics, slowly shifting the calibration of the very instruments a spacecraft depends on. A star tracker accurate to a fraction of an arc-second at launch may drift slightly out of calibration after years of radiation exposure, introducing small, hard-to-detect errors into every position calculation it makes afterward. Dust particles, though incredibly sparse, still occasionally strike a spacecraft's surface at meaningful fractions of light speed, enough energy to cause real damage or an unpredictable tiny nudge to the trajectory. None of these effects are dramatic on their own, but navigation over interstellar distances isn't broken by one dramatic failure. It's eroded slowly by dozens of small, easily overlooked factors, each one adding a little more uncertainty to a picture that was never perfectly clear to begin with. Gravity adds its own quiet complexity. Every star a spacecraft passes near, even at a distance of many light years, exerts some small gravitational influence on its trajectory. Most of the time, this is negligible. But over a journey spanning decades and trillions of miles, even negligible influences accumulate, subtly bending a trajectory away from its calculated path in ways that are difficult to predict in advance, because they depend on the precise mass and position of every star along the route, many of which aren't known with perfect accuracy from Earth-based observation. Compare this reality to how deep space is portrayed in film and fiction, and the contrast is striking. In most depictions, a lost astronaut simply spots a familiar constellation and calculates a course home with a few taps on a console. A ship's computer displays a glowing arrow pointing toward Earth as though the universe came with a built-in compass. The reality is almost exactly the opposite. There is no glowing arrow. There is no simple calculation. There is only a slow, careful, constantly revised estimate built from imperfect tools, corrected whenever possible and never entirely certain. There's one more piece of this puzzle, and it reaches into the strangest corners of physics itself. The very idea of right now doesn't mean what most people assume it means once you're dealing with objects separated by vast distances. Because information, including light, can only travel so fast. Two observers moving at different speeds or separated by great distances don't necessarily agree on what's happening at the same moment. This isn't a limitation of our instruments. It's a fundamental feature of how space and time are woven together. For someone traveling at a significant fraction of light speed deep in interstellar space, the concept of Earth's current position becomes genuinely slippery, in a way that has nothing to do with measurement error and everything to do with the structure of reality itself. There simply isn't a single universally agreed upon answer to the question of where Earth is right now, once right now stops meaning the same thing to every observer. It's a strange, almost dizzying idea, but it underscores just how deep this problem really goes. It isn't solely an engineering challenge waiting for a clever enough solution. Part of it is woven into the basic physics of the universe. Let's go back to the pulsar navigation test for a moment, because the full details matter. The experiment flew on the International Space Station, using an instrument originally built to study neutron stars for purely scientific reasons. Engineers realized it could also work as a navigation tool. They selected several millisecond pulsars, each one spinning with a rotation period known to extraordinary precision, some completing hundreds of rotations every second, more consistent over time than almost anything else in nature. By carefully timing pulses from 4 different pulsars and comparing the tiny differences in when each pulse reached the station, onboard software calculated the station's position independently. No GPS, no radio contact with the ground. The test succeeded, placing the station within a few miles of its known, verified orbit, entirely through timing signals from collapsed stars thousands of light years away. But scaling that success up to a real interstellar mission introduces problems the orbital test never faced. On the station, the instrument had a stable platform, plenty of time to gather data, and a known starting position to help calibrate readings. A spacecraft racing through interstellar space at a meaningful fraction of light speed would have none of those luxuries. It would need to gather enough X-ray photons from faint, distant sources while moving, dealing with its own vibration and accounting for extreme velocity, distorting the timing of every pulse it detects. Faint signals take real time to accumulate, and a fast-moving spacecraft can't afford to sit still and listen. This doesn't make pulsar navigation useless. It simply means it's one tool among several, powerful in principle, but still requiring significant advances before it could serve as a spacecraft's sole means of finding its way through interstellar space. History already gave us a preview of navigation under pressure, much closer to home but still instructive. During the Apollo 13 mission, an oxygen tank explosion crippled the spacecraft roughly 200,000 miles from Earth, forcing the crew to fight simply to get home alive. With their primary navigation computer partially disabled to conserve power, the crew and mission control had to improvise a way to confirm the spacecraft's orientation, using nothing more than the sun visible through a window, lined up against a specific marking, cross-checked against known star positions. It worked, but it required extraordinary precision, calm nerves, and a huge amount of support from a team on Earth able to communicate with the crew in a matter of seconds. Even then, close to home, with Earth clearly visible as a blue marble growing steadily larger in the window, the margin for error was razor thin. Now imagine that same kind of crisis occurring not 200,000 miles from Earth, but 200,000 times farther, in true interstellar space. No blue marble in the window, no quick radio exchange, no way to visually confirm orientation against anything familiar at all. The tools that saved Apollo 13 simply wouldn't exist. There's a particular piece of human history that captures this entire problem in a single poetic gesture. When Voyager 1 and Voyager 2 were launched, each carried a golden record, a message intended for any civilization that might someday find it drifting through interstellar space. Etched onto the cover of that record is a map showing the position of our Sun relative to 14 specific pulsars, each identified by its precise rotational period at the time of launch. It's essentially a cosmic return address, built using the very same pulsar timing principles that modern engineers are now trying to develop into a practical navigation system. The fact that scientists in the 1970s chose pulsars out of everything in the universe to mark our location says something important. Even then, they understood that ordinary landmarks, ordinary coordinates, mean nothing across such vast distances and such vast stretches of time. They needed something durable enough to survive the drift of every closer, more familiar reference point. But even that address comes with a caveat the designers were well aware of. Because pulsars slow down gradually as they age, the timing encoded on the record will very slowly become less accurate the farther into the future it's read. Even humanity's carefully designed cosmic return address has a kind of expiration date, a slow drift toward inaccuracy built into the physics of the very stars it depends on. Let's talk about the human side of this problem. because it's easy to get lost in instruments and equations. Researchers have studied isolation using environments that mimic some aspects of deep space. Submarine crews spending months underwater, cut off from regular contact, have reported disorientation, difficulty tracking time, and a strange detachment from familiar routines. Researchers stationed in Antarctica through the long polar winter have described similar effects, along with measurable changes in mood, sleep, and cognitive performance. Even astronauts on the International Space Station, just a few hundred miles from Earth, with a clear view of the planet and near constant contact with mission control, have described a persistent, subtle disconnection from ordinary human rhythms. Researchers sometimes call it space fog, a kind of mental haze that develops during extended time away from Earth's familiar cues. Every one of these environments still offers something deep space wouldn't. A horizon, however distant. A planet, however small, visible somewhere in the sky. A returning signal, however delayed. Strip all of that away completely, and you're left with a darkness that has no edges, no passing scenery, and no reliable way to sense your own motion through it at all. Layered on top of every technical challenge we've already discussed, it becomes clear why deep space navigation can never rely on instinct or observation the way navigation on Earth always has. Let's go back to the numbers, because understanding the true scale of the search problem helps explain why this challenge is so much harder than it first appears. Imagine a spacecraft returning from a journey 4 light-years out and 4 light-years back. Even with every navigational tool available, dead reckoning, star tracking, pulsar timing, all combined and cross-checked, realistic estimates of accumulated positional uncertainty over such a journey could easily range from tens of millions to hundreds of millions of miles, depending on how well each system performed and how many small, unaccounted forces nudged the spacecraft off its calculated path. A search radius of even 10 million miles represents a volume of space enormous enough to contain thousands of Earth-sized planets with room to spare. All of it would need to be scanned patiently, straining to detect a small, faint, reflective object against the overwhelming blackness. And that's assuming the uncertainty stays relatively small. Larger accumulated errors could push that search radius into the hundreds of millions of miles, an area so vast that locating a single planet inside it without additional guidance could take years of careful searching. This is why any realistic vision of deep space return doesn't rely on visual searching alone. It relies on some combination of advanced radio broadcasts, pre-agreed rendezvous coordinates, and enormous reserves of patience, none of which changes the underlying truth. Home, once you've left it far enough behind, becomes something you have to painstakingly relocate, not something you can simply see and steer toward. Scientists have proposed a number of ideas that might someday close this gap, though all of them remain firmly in the realm of future technology. One idea involves networks of powerful lasers positioned throughout the solar system or beyond, capable of sending extremely precise, tightly focused beams to a returning spacecraft, allowing far more accurate ranging than radio signals alone can provide. Another involves deploying small, long-lived beacon satellites at key points along likely interstellar travel routes, artificial lighthouses at chosen locations that would reduce the enormous gap between departure and destination into a series of shorter, more manageable legs. A third idea, still largely theoretical, involves quantum sensors capable of measuring motion and rotation with a precision far beyond what today's gyroscopes and accelerometers can achieve, potentially reducing the rate at which dead reckoning errors accumulate. None of these are ready today. Each faces enormous engineering, financial, and physical hurdles. But together, they represent the general direction Serious researchers believe this problem will need to be solved, not through a single breakthrough, but through several complementary systems working together, each one covering for the weaknesses of the others. There's also a broader, quieter consideration that applies specifically to any journey long enough to stretch across multiple human generations. If a voyage lasted so long that the people who eventually attempted to return were the descendants, not the original travelers, the very idea of home might mean something entirely different to them. Culture drifts, memory fades, stories passed down through generations change with each retelling. A crew born and raised entirely aboard a ship, having never seen Earth, having only heard about it through inherited stories and preserved records, might not experience the pull of home the same way their ancestors did. The navigational problem would remain exactly as difficult, but the emotional weight behind solving it, the urgency, the longing, might fade along with everything else that gets lost across so many generations spent adrift. Distance in space doesn't just separate people from a place. Over long enough timescales, it can separate people from the very meaning that place once held. One final piece of context helps tie all of this together. It involves how astronomers actually build the star catalogs that spacecraft navigation depends on in the first place. A space telescope named Gaia, launched by the European Space Agency, spent years precisely measuring the positions, distances, and motions of nearly 2 billion stars across the galaxy. It produced the most accurate map of the night sky ever created. Each new release of Gaia's data has steadily improved the precision available to spacecraft navigation systems. But even a map that detailed is by necessity a snapshot, a single moment frozen in an ever-changing sky. Every star in that catalog continues moving after the measurement is taken. The catalog has to be periodically updated to stay useful, especially for missions expected to operate far into the future. For a mission lasting a few years, this isn't a major concern. For a hypothetical mission lasting decades or centuries, even the finest star catalog ever produced would need to be treated as a starting point, not a permanent, unchanging truth. There's an entirely different category of proposed interstellar mission worth considering, because it faces this same problem in an even more extreme form. Several research groups have proposed sending tiny spacecraft, some no larger than a postage stamp, attached to ultra-thin sails and pushed to a meaningful fraction of light speed using powerful ground-based lasers. A spacecraft that light needs far less propellant can be accelerated far more easily and could theoretically reach a nearby star system in a couple of decades. But that small size comes with a brutal trade-off. There's almost no room for heavy, power-hungry navigation instruments, no large star trackers, no powerful transmitter capable of sending a strong signal back across light years, no room for a pulsar timing instrument sensitive enough to gather usable data. These tiny probes are largely designed to be one-way messengers, gathering what data they can during a brief high-speed flyby and transmitting it back toward Earth. The idea of such a probe ever navigating its way home isn't really part of the design at all. For missions like these, the challenge of finding your way home doesn't just get harder. It gets set aside almost entirely, replaced by a different goal: sending information home rather than bringing the spacecraft itself back. Generation ships face the opposite problem. They're big enough to carry sophisticated navigation equipment, potentially redundant systems, multiple star trackers, backup gyroscopes, dedicated pulsar timing instruments. But their journeys are so much longer. Even the best instruments face accumulated drift, radiation damage, and calibration decay compounded across far more time than any spacecraft humanity has ever built and operated continuously. A probe only needs to stay accurately navigated for a matter of years. A generation ship would need every part of its navigation system, and the humans responsible for maintaining it, to remain reliable across a span of time longer than most technologies in human history have ever remained in continuous use. Every navigational challenge would need to be solved not once, but repeatedly, generation after generation, by crew members who may never fully trust instruments built by engineers who lived centuries before they were born. Let's spend a little more time with the strangest consequence of high-speed travel. Picture two people, identical in every way. One staying on Earth, the other boarding a spacecraft capable of reaching a significant fraction of light speed. The traveling twin heads out toward a distant star, spends some time there, then turns around and heads back. From the perspective of the twin who stayed behind, the round trip might take 10 years. But from the perspective of the traveling twin, because of time dilation at high speed, only a few years might have passed on board. When the traveling twin returns, they step off the spacecraft younger, in a real, physically measurable sense, than the twin who never left. This isn't science fiction. It's been directly measured using precise atomic clocks flown on airplanes and compared to identical clocks left on the ground. Scale that same effect up to the speeds required for interstellar travel, and the difference stops being a fraction of a second. It becomes years, potentially decades, depending on how fast and how far the journey goes. This is why the challenge of finding your way home in deep space isn't only about spatial coordinates. It's about time as well. Even a perfectly calculated position, matched exactly to where Earth will be when you arrive, still delivers you into an Earth that is aged years beyond what you experienced during your journey. You're not just navigating through space. You're navigating into a future version of home that you never got to watch unfold, arriving as a kind of visitor from the past, disconnected from everything that happened while you were away. Now let's zoom out to a scale even larger than an individual journey, because home itself is embedded in motion at every level. Our sun, carrying Earth and the rest of the solar system along with it, orbits the center of the Milky Way roughly once every 230 million years. At the heart of that orbit sits a supermassive black hole, Sagittarius A, around which the entire galaxy slowly rotates. The last time our solar system completed one full lap around that distant galactic center, there were no flowering plants on Earth. No birds, no mammals resembling anything alive today. Zoom out even further, and the picture becomes stranger still. Space itself, the very fabric that distances are measured across, is expanding, stretching gradually in every direction. This expansion is negligible at the scale of a single galaxy, far too small to affect anything happening within the Milky Way. But it's a reminder of just how many layers of motion are stacked on top of each other. From a planet spinning, to a solar system orbiting a galactic center, to galaxies drifting apart across the largest scales imaginable. Nothing in this universe, at any scale, holds still. Home was never a fixed dot. It was always a point riding along inside a nested series of enormous ongoing movements. Deep space simply removes the illusion that let us ignore that fact. The tracking system that keeps our actual spacecraft found shows just how much infrastructure is required even for missions that never leave the solar system. NASA's Deep Space Network relies on 3 complexes spaced roughly 1/3 of the way around the globe from each other. One in California, one in Spain, one in Australia. As Earth rotates, at least one complex is always facing whichever direction a distant spacecraft happens to be. Each complex uses massive dish antennas, some over 200 feet across, capable of detecting radio signals of almost unimaginable faintness. The total power received from something like Voyager, after traveling billions of miles, measures in fractions of a billionth of a watt. The combined power collected from Voyager's signal across an entire year of listening, wouldn't be enough to power a small light bulb for even a fraction of a second. Detecting a signal that faint requires extraordinarily sensitive receivers, careful filtering of background noise, and enormous antennas working in precise coordination. Now push that same signal out to the distances involved in true interstellar travel, tens of trillions of miles instead of billions, and the mathematics become almost absurd. A signal that weak, spread across a distance thousands of times greater, would require either an enormously more powerful transmitter than any spacecraft could realistically carry, or a receiving antenna on Earth so large it would dwarf anything currently in existence. This is part of why any realistic interstellar mission concept assumes communication will become sparser and sparser the farther a spacecraft travels. Not because engineers choose to communicate less, but because physics itself makes frequent detailed communication increasingly, and eventually completely, impractical. Picture what an actual multi-decade solo journey into deep space might genuinely feel like, stripped of dramatic embellishment, based only on what we've covered. Weeks after leaving the solar system, the sun itself would begin shrinking into just another point of light among the stars. No longer a disk, no longer something that provides warmth or a clear sense of direction, just one more distant light among thousands. Communications with Earth would grow slower and slower, each message a fading transmission from a version of home growing further out of reach with every passing year. Instruments would require constant, careful monitoring, cross-checking star positions against onboard catalogs, watching for subtle signs of gyroscope drift, waiting patiently for faint pulsar signals to accumulate into something usable. Every calculation would carry a small, honest acknowledgement of uncertainty, a margin of error growing a little wider each passing month, never quite resolving into the kind of confident certainty that a compass or a road sign offers here on Earth. And at the far end of that journey, whenever the decision came to turn around, the destination waiting at the other end wouldn't simply be Earth. It would be an Earth that had kept moving, kept aging, kept changing in ways impossible to know from so far away. For the entire time its traveler had been gone. There's a technique engineers use today to pin down a spacecraft's position with even greater precision than simple round-trip timing allows. It's called very long baseline interferometry. Instead of relying on just one antenna, engineers use 2 or 3 widely separated dishes, sometimes on different continents, to receive the same signal from a distant spacecraft at very slightly different times. The signal travels a tiny bit farther to reach one antenna than another. Engineers measure that tiny timing difference and compare it against the known distance between the antennas, allowing them to calculate the spacecraft's direction in the sky with remarkable accuracy. Combined with distance measurements from round-trip timing, this gives mission control an extremely precise 3-dimensional fix on a spacecraft's position. It's elegant. It's part of why we can track something as small and as far away as Voyager 1 with such confidence. But notice once again what this method fundamentally depends on. Multiple fixed antennas here on Earth, precisely surveyed, precisely synchronized, working together as a single enormous instrument. Stretch the communication delay out to years, and this technique stops being useful for real-time navigation the same way every other Earth-based method does. Timing itself introduces yet another quiet complication, because every navigation method we've discussed depends on extremely precise clocks. And clocks, even the best ones humans have ever built, aren't perfectly immune to drift. Atomic clocks measure time using the extremely consistent vibrations of atoms, typically cesium or rubidium. The best examples would lose less than a single second over hundreds of millions of years. But a spacecraft's onboard clock and the clocks used by tracking stations on Earth aren't physically the same device. They have to be synchronized periodically using signals sent back and forth. Any tiny mismatch translates directly into a tiny error in every distance calculation that depends on precise timing. Relativity adds an extra twist here, too. A clock moving at high speed, relative to another clock, genuinely ticks at a different rate, not due to mechanical imperfection, but due to time dilation. A clock on board a spacecraft traveling at a meaningful fraction of light speed would need to be continuously, carefully adjusted to stay synchronized with clocks back on Earth. Any small error in that adjustment ripples outward into every position. Calculation the mission depends on. There's also a very practical, unglamorous limitation sitting underneath all of this. One that has nothing to do with instruments or physics and everything to do with basic engineering reality. Fuel. Every correction to a spacecraft's trajectory, however small, requires firing thrusters. And every thruster firing consumes propellant that can never be replaced once a mission leaves Earth. For missions within the solar system, this balance is manageable. For a journey lasting years or decades across interstellar distances, the balance becomes far more delicate. Every correction burns propellant that a returning traveler might desperately need later, especially if unexpected drift or instrument errors require larger, more urgent corrections near the end of an already fuel-depleted journey. In principle, you could carry more fuel to allow more corrections. In practice, more fuel means more mass. And more mass means needing even more fuel just to accelerate that extra weight. A compounding trade-off engineers call the tyranny of the rocket equation, one of the most stubborn, unavoidable constraints in all of spaceflight. Contrast all of this with how human navigators succeeded for thousands of years without any modern instruments at all. Polynesian navigators sailing across the vast Pacific Ocean centuries before written charts or compasses developed an extraordinarily sophisticated system of wayfinding. They used the rising and setting points of specific stars, the direction and pattern of ocean swells, the behavior of seabirds, and the color of the sky to guide voyages across thousands of miles of open water with remarkable accuracy. One of the most impressive navigational achievements in human history, built entirely on close, patient observation of a consistent, repeating environment. But notice what made it work. The stars rose and set in predictable patterns because Earth was rotating steadily beneath a sky that, for practical purposes, held still. The ocean swells were generated by predictable nearby weather patterns and coastlines. The birds they tracked were returning to islands that stayed exactly where they'd always been. Deep space offers no repeating horizon, no consistent nearby landmarks, no seabirds returning to a fixed island. It offers only distant points of light shifting subtly with your own velocity, and an unforgiving, unblinking silence in every direction. The very ingenuity that let ancient sailors conquer the largest ocean on Earth simply has nothing to work with once the environment itself stops holding still. Given how many of these problems stem from the delay in getting help from Earth, some researchers have proposed shifting more navigational decision-making onto the spacecraft itself. Rather than waiting years for instructions from mission control, an autonomous system using onboard artificial intelligence could theoretically analyze star tracker data, pulsar timing, and dead reckoning estimates, then make its own real-time decisions about small course corrections without waiting for confirmation. Early versions of this kind of autonomous navigation have already been tested on missions much closer to home. Extending that same independence to a true interstellar mission is appealing because it removes the crippling communication delay from the decision-making loop entirely. But it doesn't remove the underlying uncertainty. An onboard AI system would still be working with the exact same imperfect inputs: drifting gyroscopes, shifting starlight, faint and inconsistent pulsar signals. Removing Earth from the loop makes decisions faster. It doesn't make the underlying information any more accurate. In some ways, it simply shifts the burden from a team of engineers on Earth to a computer millions of miles away, still working with the same fundamentally imperfect tools. There's one more version of this problem worth considering, because it strips away Earth entirely and asks a slightly different question. Imagine two separate spacecraft, both traveling through deep space, both wanting to find each other and meet at some agreed location. Neither one has a fixed point to measure against. Both are moving. Both carry their own small accumulating navigational errors. Both are trying to calculate not just their own position, but the position of another object that's equally uncertain about where it is. This is, in a sense, the purest version of the entire problem, stripped of the comforting idea that at least one side of the equation might hold reasonably still. Two moving, uncertain points, trying to locate each other across an empty, referenceless expanse. It only gets harder as the distances grow larger and the available reference points grow sparser. It's a small, elegant illustration of just how much ordinary navigation quietly depends on having at least one thing that isn't moving relative to everything else, and how rare that condition becomes once you're truly out among the stars. It helps to think of this entire problem as a gradient rather than a sharp line that's either crossed or not, because difficulty increases steadily the farther you travel. Navigating to the moon, 250,000 miles away, is manageable with communication delays measured in a couple of seconds. Navigating to Mars stretches those delays to between roughly 4 and 24 minutes one way. Mission controllers can no longer react instantly, but meaningful corrections still arrive within the same day. Spacecraft heading to Mars already rely heavily on pre-calculated trajectories and onboard systems capable of short-term independent decisions. A small preview of the independence a true interstellar mission would need on a vastly larger scale. Navigating to the outer planets stretches delays to tens of minutes or hours. Earth begins shrinking into just another point of light. Navigating to the edge of the solar system stretches round-trip communication to nearly a full day. Earth becomes indistinguishable from background stars without instruments specifically designed to locate it. Interstellar space simply continues that same trend to its logical conclusion. Every single challenge discussed tonight already exists in smaller form within our own solar system. Interstellar travel doesn't introduce a fundamentally new kind of problem. It simply removes every remaining safety margin that makes those same problems manageable closer to home. Signal strength follows an unforgiving mathematical rule that makes this gradient even steeper than distance alone would suggest. Radio signals, like light, spread out in every direction as they travel, weakening according to what's called the inverse square law. Double the distance a signal travels, and its strength drops to 1/4 of what it was, not half. Triple the distance, and strength drops to 1/9. This is why the faint whisper from Voyager, already billions of miles away, requires some of the most sensitive receiving equipment ever built just to detect it all. Push that same signal out to true interstellar distances, tens of trillions of miles instead of billions, and the mathematics become almost absurd. Frequent, detailed communication doesn't become difficult. It becomes, eventually, physically impossible. There's an interesting parallel that runs in the opposite direction, involving humanity trying to be found rather than trying to find its way home. In 1974, scientists used the massive radio telescope at Arecibo in Puerto Rico to broadcast a deliberately designed message toward a distant cluster of stars. It encoded basic information about humanity, our numbers, our chemistry, our solar system, sent toward a target roughly 25,000 light-years away. Even if it's received, understood, and a response is sent back immediately, the entire round trip would take 50,000 years. That message represents the flip side of the exact problem we've spent tonight exploring. If humanity ever wanted to be found, Ever wanted some future traveler, human or otherwise, to know where home is located? We'd face the same fundamental obstacle, trying to communicate a fixed address across a universe where nothing holds still long enough to have one. The Arecibo message, like the golden records aboard the Voyager spacecraft, had to rely on the same imperfect solution we've returned to again and again tonight. Pulsar positions, relative rather than absolute coordinates. An approximate address built from the least unreliable landmarks the universe happens to offer. Let's pull every thread together into one place. Because taken individually, each piece might seem like a solvable engineering hurdle. Dead reckoning accumulates small errors into large ones over years of travel. Star tracking distorts as stellar aberration and proper motion shift the very reference points a spacecraft depends on. Radio contact with Earth becomes a conversation with the past, arriving too late to offer real-time guidance across true interstellar distances. Pulsar navigation, while promising, requires long observation times and remains vulnerable to the same relativistic distortions affecting everything else. Magnetic navigation disappears entirely beyond the heliosphere. Inertial instruments drift steadily over time, with no interstellar mission yet capable of correcting that drift over decades without external help. Radiation and dust slowly degrade the very sensors a mission depends on. Gravitational influences from passing stars subtly bend a trajectory in ways difficult to predict. Fuel constraints limit how often and how significantly a spacecraft can correct its course. And underneath every one of these individual problems sits the deepest issue of all. The simple, well-established fact that the universe contains no fixed, absolute reference point for anything to measure itself against in the first place. Each of these problems on its own might be manageable. Engineers are resourceful, and individual technical obstacles tend to yield eventually to patient incremental progress. But navigating home from deep space isn't one problem. It's all of these problems stacked together, compounding simultaneously over a time scale and a distance that pushes every one of them to its absolute limit at the same time. There's a visual effect tied to high-speed travel that adds one more layer of distortion on top of everything already discussed. At a significant fraction of light speed, light doesn't just shift in color. It also appears to concentrate, brightening dramatically in the direction of travel while fading in the direction you've come from. An effect sometimes called relativistic beaming. Stars scattered evenly across the sky before departure would begin to visually crowd toward the forward direction as speed increased, growing brighter and more tightly clustered directly ahead. The sky behind would grow dimmer and sparser until, at extreme enough speeds, it would appear almost completely dark. The entire visual backdrop a traveler might instinctively rely on for a rough sense of orientation would look nothing like the sky charted before launch, distorted in a precise, predictable, yet deeply unfamiliar way tied directly to the ship's own velocity. Given how many independent sources of error we've covered, engineers manage uncertainty in practice by never trusting any single method completely. Real spacecraft navigation, even for missions well within the solar system, rarely relies on just one technique. Dead reckoning estimates are constantly cross-checked against star tracker readings. Star tracker readings are cross-checked against radio ranging from Earth. Any available pulsar timing data gets folded in as an additional independent check. When two or more independent methods agree closely, confidence in the calculated position goes up. When they disagree, engineers know something is wrong, even if they can't immediately tell which system is at fault. That disagreement itself becomes valuable information, prompting careful investigation rather than blind trust in any single readout. This layered cross-checking approach is in many ways the most honest solution humanity currently has. Not a single perfect answer, but a patchwork of imperfect methods, each one covering for the blind spots of the others, constantly compared to catch mistakes before they compound into something dangerous. not elegant, but resilient. The same way a chain made of several slightly weak links can still hold, as long as enough of those links happen to be strong at any given moment. There's a physical, bodily dimension to disorientation in deep space that goes beyond simply lacking visual landmarks. It involves the inner ear. Human balance relies heavily on a small, fluid-filled structure inside the ear called the vestibular system, which detects motion and orientation relative to gravity. In the weightlessness of orbital spaceflight, astronauts commonly experience a period of adjustment as their vestibular system, receiving no clear gravitational signal, struggles to reconcile what it senses with what their eyes are telling them. Over time, most astronauts adapt, learning to rely more heavily on visual cues. But that adaptation still depends on having reliable visual cues available. In deep space, far from any nearby planet, moving at extreme speed through a visually distorted sky, even those compensating visual cues become unreliable. That leaves both the inner ear and the eyes struggling to agree on any stable sense of orientation at all. A small, easily overlooked detail, but one that illustrates just how much of ordinary human navigation depends on cues that simply don't exist once you're far enough from anything familiar. Given everything we've covered, there's one more idea that quietly sidesteps the entire problem rather than solving it. Some mission concepts, particularly those involving generation ships or other extremely long-duration voyages, aren't designed around the idea of returning at all. They're designed for one-way settlement, carrying people toward a new home rather than attempting the far more complicated return journey. In a strange way, this approach avoids nearly everything we've discussed tonight, not by solving the navigational challenge of finding your way back, but by removing the need to ever attempt it. There would still be enormous challenges in accurately reaching a chosen destination. All the difficulties of dead reckoning, star tracking, and long-term instrument drift still apply on the outbound leg. But at least there would be no return trip demanding a second, even more uncertain calculation. It's a pragmatic, if sobering, acknowledgement of just how difficult the return half of this problem really is. Sometimes the most realistic answer to an almost impossible challenge isn't a clever new technology. It's choosing not to attempt the hardest part of the journey at all. There's a well-documented psychological phenomenon that astronauts have described after seeing Earth from space. Researchers call it the overview effect, a profound shift in perspective that comes from watching our planet hang alone against the blackness. A small, fragile, borderless sphere with no visible lines separating countries. No visible evidence of the conflicts that seem so significant from the surface. Astronauts who've experienced this consistently describe a deepened sense of Earth's fragility and a stronger emotional connection to it as a single unified home. That experience depends on something we've spent this entire exploration establishing doesn't exist in true deep space, a visible nearby Earth to look back at. Every astronaut who has described the overview effect experienced it from orbit or at most from the distance of the Moon, still close enough to see Earth as a recognizable whole world. A traveler far out in interstellar space wouldn't have that option. Earth from that distance isn't a blue marble hanging in a window. It's an indistinguishable point of light buried among thousands of other points of light, requiring careful calculation just to identify which one it even is. The very experience that has moved so many astronauts to describe a renewed sense of connection to home would become unavailable exactly when a traveler might need that connection most. The uncertainty we've discussed isn't a fixed, unchanging number. It grows continuously the entire time a spacecraft is traveling, spreading outward the way ripples widen on a pond, except in 3 dimensions, without ever settling back down. At the start of a journey, position is known with excellent precision, carefully calibrated before departure. A year in, small errors have begun to accumulate but remain modest. A decade in, without frequent precise correction, that uncertainty has grown substantially, no longer a tight, confident dot on a map, but a widening region of possible positions. Multiple decades in, deep into a genuine interstellar journey, that region could easily encompass millions of miles in every direction. A fog of possibility rather than a single known point. This is the fundamental shape of the entire problem explored tonight. Not a single moment of being lost, but a slow, continuous drift away from certainty, compounding quietly with every passing year, regardless of how carefully each individual instrument was built, or how skillfully each individual correction was calculated. There's a reason this particular challenge, more than almost any other aspect of interstellar travel, tends to get glossed over in popular imagination. Faster than light travel, artificial gravity, suspended animation. These are all dramatic, visually compelling problems with equally dramatic, imaginable solutions. Navigation, by comparison, feels mundane. A background detail rather than a headline challenge. But as we've seen tonight, it might actually be one of the most stubborn, deeply rooted problems facing any realistic vision of deep space travel. Not because it lacks a clever technological fix, but because it's tangled up with some of the most fundamental features of the universe itself. The absence of any fixed reference frame, the finite speed of light, the reality of time dilation, the sheer overwhelming scale of the distances involved. Every other challenge in space travel, propulsion, life support, radiation shielding, is at its core an engineering problem. Difficult, but theoretically solvable with enough time, funding, and ingenuity. Navigation across true interstellar distances is partly an engineering problem too. But underneath all the engineering lies something that engineering alone can't fully resolve. A universe that was simply never built with a fixed address system in mind, where every location only makes sense relative to other locations that are themselves in constant motion. There's one last idea. A way researchers have suggested we might soften this problem, even if we can't fully solve it. Rather than trying to relocate Earth directly from across light years, a returning mission could instead aim for a pre-computed rendezvous point, a specific location and time agreed upon before departure, calculated using Earth's well-understood orbital motion projected forward across however many years the round trip is expected to take. Instead of asking, "Where is Earth right now?" An impossible question to answer with real-time precision from that far away. The traveler would be solving a narrower, more manageable question. Where will Earth be at this specific agreed-upon future moment? That's a question orbital mechanics can answer with far more confidence, since planetary orbits are governed by well-understood, highly predictable gravitational rules. This doesn't eliminate the problem. The traveler's own position still carries all the accumulated uncertainty discussed throughout. But it does shrink the size of the target, replacing a vague, ever-moving idea of home with a specific calculable point in space and time. In a universe with no fixed points to rely on, narrowing the problem down is often the most realistic kind of progress available. History offers a striking parallel to everything we've discussed tonight, one that unfolded centuries before anyone imagined leaving Earth at all. For most of the age of ocean exploration, sailors could determine latitude, their position north or south, fairly reliably by measuring the angle of the sun or known stars above the horizon. But longitude, position east or west, remained one of the most dangerous unsolved problems in navigation for centuries. Without it, ships regularly misjudged their position by hundreds of miles on long ocean voyages, leading to shipwrecks on unexpected coastlines and vessels running out of supplies while searching for land that wasn't where their charts suggested it should be. The underlying issue was almost identical in principle to the problem we've spent tonight exploring. Determining longitude required knowing the precise time at a fixed reference location and comparing it against local time. The trouble was clocks. No timekeeping device of the era could maintain accurate time aboard a rocking, humid, temperature-shifting ship for months at sea. It would drift by minutes or hours, and a small error in time translated directly into a large error in calculated position. It took decades of dedicated effort and the development of an entirely new kind of mechanical clock specifically engineered to remain accurate despite motion, temperature changes, and humidity, before reliable longitude calculation finally became possible. The parallel to deep space navigation is almost exact, separated only by scale. Just as 18th century sailors needed an extraordinarily precise, stable clock to solve the longitude problem, any realistic interstellar mission needs extraordinarily precise, stable timing, whether from atomic clocks or pulsar signals. The same fundamental challenge, figuring out a precise position using nothing but careful, patient measurement against a moving, imperfect set of references. It took roughly 40 years of dedicated refinement to solve the ocean-going version. There's no reason to assume the interstellar version will resolve any faster, given the scale involved. Trillions of miles instead of thousands, years of communication delay instead of weeks. It may well demand an even longer, more patient process of incremental refinement before anything resembling a reliable, trustworthy solution exists. Every spacecraft humanity has ever launched, no matter how far it's traveled, has remained in some fundamental sense on a tether to Earth. A thin, patient thread of radio contact stretching across the growing distance, kept alive by an entire network of engineers, antennas, and carefully maintained infrastructure back home. Voyager 1, even now drifting through interstellar space more than 15 billion miles away, still checks in. Its faint signal still reaches the giant dishes of the deep space network. Still gets decoded, still gets logged, still gets answered. Even if that answer takes more than a day to arrive. That tether is thin, strained by distance, weakened by time. But it hasn't broken. A true interstellar traveler, venturing far enough and staying gone long enough, would eventually reach a point where even that thin tether becomes meaningless. The delay grows so long and the signal grows so faint that Earth stops being a place you can meaningfully communicate with at all. It becomes instead a place you can only calculate toward, using nothing but memory, mathematics, and hope. So where does that leave us? If dead reckoning drifts, if starlight bends and shifts the faster you move, if pulsar timing still carries its own uncertainties, if radio contact becomes a conversation with the past rather than the present, and if even with a perfect fix on your position, the destination itself will have aged and moved on without you, then the honest answer is this. Finding your way home from deep space isn't a solved problem. It's a layered one, made up of several partial solutions stacked on top of each other, each one narrowing the uncertainty a little, none of them eliminating it completely. Engineers today combine dead reckoning with star tracking with radio ranging from Earth, radio ranging with pulsar timing where possible, and constant correction whenever new data becomes available. For missions within the solar system, this layered approach works remarkably well. But for a true interstellar journey, one lasting decades, crossing trillions of miles, moving fast enough for relativity itself to start bending the rules, every one of those methods weakens simultaneously. And no one has yet designed a system capable of holding all of them together with the precision such a journey would demand. Maybe someday that changes. Maybe future navigation systems will combine pulsar timing with new kinds of quantum sensors. Maybe entirely new reference points will be discovered, giving future travelers something steadier to measure themselves against. But right now, today, with the technology and understanding we actually have. The truth is simple and a little humbling. The farther you travel from Earth, the less the universe gives you to hold on to. Space doesn't offer road signs. It doesn't offer landmarks. It offers a handful of imperfect tools, a few clever tricks borrowed from centuries of ocean navigation, and an unforgiving amount of distance in every direction. Home isn't a coordinate frozen in space, waiting patiently for you to find your way back to it. It's a moving point carried along by a spinning planet, orbiting a moving star inside a moving galaxy, drifting through an expanding universe. By the time you'd worked out exactly where it used to be, it would already be somewhere else. And that, more than any single technical obstacle, is the real reason no one could simply turn around and fly home from deep space. Not because we lack the courage, not because we lack the ingenuity, but because the universe itself refuses to hold still long enough to let us. Start with a simple question. Where is Earth right now? You might think the answer is obvious. Earth orbits the Sun, 93 million miles out, tracing the same path it always has. But that answer is missing almost everything that matters. Earth is spinning on its axis at over 1,000 miles per hour at the equator. It's circling the Sun at roughly 67,000 miles